Have you ever really stopped to wonder how a computer actually thinks? Today, we're diving deep into that very question, pulling from some fantastic research material developed for educators by Dr. Sudheendra S G. We're getting right to the core of how a machine, a literal box of rocks we tricked into thinking, does math.
I mean, we completely take it for granted, right? Every single photo you edit, every video game you play, every spreadsheet that crunches numbers, it all boils down to basic math. But how does a chunk of silicon and metal actually, do math?
Well, the secret isn't some huge, complex system spread all over the place. Nope. It's actually concentrated in one incredibly elegant, powerful, and absolutely critical little piece of engineering. And it has a name, the ALU. That stands for the Arithmetic and Logic Unit. If you think of the main processor, the CPU, as the computer's brain, then the ALU is the specific part of that brain that does all the heavy lifting for math and for making decisions. It is the absolute engine of all computation. So, to really get our heads around this mathematical brain, we need to look at how it splits its work. It basically has two very different but equally vital jobs. Okay, think of it like this. The arithmetic unit. That's your calculator. It handles the raw numbers, adding, subtracting, all that good stuff. But the logic unit, it's more like an umpire. It doesn't crunch numbers itself. It compares them and makes a call. Is this bigger than that? Are these two things the same? It's the decision maker.
And, this little component was a total game changer. Before 1970, you needed a whole circuit board, a big, clunky thing just to do these calculations. Then, Intel came along with the 74811 and put the entire mathematical brain onto a single tiny chip. This completely revolutionized electronics as we know it.
So how in the world does it actually work? Well, it all starts with the most basic, fundamental operation you can imagine. We're going to build our understanding from the ground up, starting with just a single bit.
When you add two bits, there are only four possible outcomes. The first three are super simple. 0 plus 0 is 0. 1 plus 0 is 1. No problem. But that last one, 1 plus 1. In binary, the answer is 1, 0, which is how a computer writes the number 2. This gives us two results, a sum of 0 and a carry of 1 that we have to pass to the next column, just like when you learn to add in school.
So how does a circuit get two different answers from the same problem? It uses something called logic gates. You can think of them as tiny automatic switches that make really simple true or false decisions. And it just so happens that two specific dates are perfect for this job. An XOR gate gives us the correct sum every single time. And an AND gate is perfect for spotting that one special case, the 1 plus 1, where we need to carry the 1. And just like that, by wiring up these two gates, we've created our very first building block. It's a circuit called a half adder. It can successfully add two bits and tell us both the sum and whether we need to carry a 1. But, as the name implies, that's only half the story. A half adder is great, but it's only good for adding single bits. We live in a world with much bigger numbers, so for that, we're going to need a more powerful tool. And here it is, the full adder. Its superpower is that it can handle three inputs, our two bits, A and B, plus a potential carry bit that's coming in from the calculation next door. This ability to accept a carry-in is the absolute key to adding numbers of any size. So how do we use it? We chain them together. For an 8-bit number, we start with one half adder, and then we line up 7 full adders right after it. The carry bit from the first addition literally ripples down the line to the next one, which calculates and sends its carry to the next, like a series of dominoes falling one after another. This 8-bit adder is powerful, but it does have a limit. With 8 bits, the biggest number you can possibly represent is 255. So what do you think happens if you try to add one more? You get an overflow. And here is one of the best real-world examples ever. The level counter in the original Pac-Man arcade game was an 8-bit number. So when gamers got good enough to reach level 256, the ALU's adder just couldn't handle it. The number was too big, it overflowed, the game's code completely broke, and half the screen turned into a mess of graphical garbage. An ALU limitation became a legendary gaming challenge. Okay, so addition is clearly the foundation of everything, but the ALU is not a one-trick pony. It handles other kinds of math, and, just as crucially, it makes those logical decisions we talked about. So what about something like multiplication? Well, in its simplest form, an ALU doesn't even have a special part for multiplying. It just does addition over and over and over again. Now, the modern processor in your phone has all sorts of specialized circuits to make this way faster, but at its very core, it's all built on that humble adder we just designed. And here's that other half of the brain, the logic unit. This is where those simple operators like and, or, and not live. Think about a video game again. The software is constantly checking things like, has the player pressed the jump button and is the character currently on the ground? Those simple logical tests are the building blocks for all complex decision-making in every piece of software you use. Okay, so the ALU does its calculation, but how does the rest of the computer have any idea what happened? Did it work? Was the result 0? It can't just shout the answer. It uses this really clever system of signals. It uses something called flags. Just think of them as little one-bit status updates. After every single operation, the ALU raises or lowers these flags. If the result was 0, the 0 flag pops up. If the answer was too big to fit, boom, the overfill flag goes up, just like in Pac-Man. They're like the ALU's little emojis, instantly telling the rest of the processor exactly how the calculation went. All right, we have seen all the individual pieces now. The calculator, the umpire, and those little signal flags. So let's put it all together and watch the magic happen. This is the heartbeat of every single calculation. First, 2 numbers come in. An instruction code, an opcode, tells the ALU what to do. Add, subtract, compare. Then, the correct unit gets to work. The result is sent out. And finally, the status flags are all updated to report on the outcome. This exact 5-step cycle happens billions of times every single second inside a modern processor. It's just mind-boggling. And that's really the key takeaway here. The fundamental principles we've just walked through, from a simple half adder all the way to ripple carry adders and flags, are exactly what's happening inside that incredibly advanced chip that powers your smartphone. It's the same logic, just scaled up to a degree that is almost impossible to comprehend. So we've figured out how the computer calculates. It has a mathematical brain. But calculation is pretty useless without memory. The ALU can add 2 numbers, sure, but how does the computer remember the results? Or what instruction it's even supposed to be working on next? Well, that is a question for another time.